This program continues the aspect of geology that we began looking at last week, the economic end of the business, so to speak. We'll look at two of Canada's most important geological resources, the Athabasca tar sands and the Sudbury nickel ores. It also brings us to the 22nd and the last program in the series, and I hope that, as well as informing you, we've managed to arouse your curiosity sufficiently for you to continue thinking and doing some geology of your own. I hope that perhaps one day I'll meet some of you on outcrops. One more hour of geology. The material prosperity of a country is very much controlled by its geology. If it has greenstone belts and ancient subduction zones, then it's likely to be very well endowed with metallic ore deposits. And if on top of that it has relatively thick, undisturbed sequences of sedimentary rocks deposited in deltas and in the shallow seas of continental shelves, then it's likely to have oil and coal as well. Such a country is Canada, probably the most fortunately endowed country in the world, and that's what these two specimens have in common. This ore from Sudbury, by most standards the most productive mineral area in the world, and this tar sand from Athabasca, the largest liquid deposit of hydrocarbons in the world. We'll look at the geology of these two great deposits, beginning with the Athabasca tar sand. The prairie provinces already supply most of Canada's fossil fuel, and the 350-mile arc of tar sand in northeast Alberta is still a largely untapped resource for the future. The well-known Athabasca part of the tar sand occupies about 9,000 square miles between 55 and 58 degrees north and is cut by the Athabasca River. The center of current development is 275 miles north of Edmonton and 23 miles from the nearest town, Fort McMurray, at the junction of the Clearwater and Athabasca rivers. To the north is the Wood Buffalo National Park. A barrel of oil contains 35 Canadian gallons. The tar sand deposit as a whole is estimated to contain about 800 billion barrels of raw bitumen. The Athabasca part of the deposit contains some 626 billion barrels, which, when refined, would yield about 430 billion barrels of crude oil, which would equal about 2/3 of the world's known crude oil resources. However, current technology can only recover and refine something over half of that, which is still 1 million barrels of oil a day for 750 years. The tar sand is buried by up to 2,500 feet of overburden. Black spruce and tamarack swamp grow on about 20 feet of muskeg. Beneath that is a variable thickness of glacial gravel and Cretaceous shale and sandstone. Although removing the overburden and developing the technology for recovering the bitumen will be extremely costly, the usual expense of exploration is not a problem, because the Athabasca River has about 120 miles of tar sand exposed in its banks. Outcrops of the bitumen-bearing Cretaceous sand are black and sticky, and in the warmth of summer the bitumen oozes from cracks and bedding planes, laying down a slippery film at the water's edge. After Indians had for many years mixed the bitumen with spruce gum and patched their canoes with it, white men discovered the deposit. It's about 140 feet thick on average and varies between a minimum of 90 and a maximum of 220 feet. The deposits were first discovered in 1778 by fur traders, and there are still the scars of the excavations, the test excavations, which have been made since then. The black bitumen was quite a curiosity to many of the early explorers of the Athabasca River. One of those was a fur trader in the 18th century, in 1778, one of the most best-known explorers of the Athabasca River, Peter Pond. Since him, the list of discoverers and surveyors reads like a historical who's who. Alexander Mackenzie was the first to recognize the black bitumen for what it was, and by 1888, the Geological Survey's R.G. McConnell had thoroughly investigated the deposit and determined that it had commercial possibilities, but not for oil, instead for paving roads. And Dr. Adolf Clark developed his hot water and steam method for separating the oil and sand in the early 1920s. And today, the bush around the Athabasca tar sand is the graveyard for dozens of experimental and commercial sites. Geologically, the tar sand is a poorly consolidated sandstone deposited by a Cretaceous river which drained over and eroded into the Devonian limestone in the area about 120 million years ago. In other words, the tar sand lies on an unconformity. The limestone is clearly visible in the lower part of the banks of the river, and the unconformity is clearly marked. It's a well-bedded limestone, deposited during late Devonian time, 350 million years ago, when Western Canada was covered by a warm, shallow sea, rich in marine life, such as reef-forming corals. The bitumen of the tar sands may have originated in those limestones and later seeped upward into the sandstone, which thus acted as a reservoir for the bitumen. The limestones are about 350 million years old, and the sandstones about 120 million. So the unconformity represents a gap of perhaps 230 million years in the geological record. Above the economic tar sands is barren Cretaceous sand and shale, covered in turn by the sand and gravel left by the glacial ice which melted away from here about 15,000 years ago. The present mining technique is open pit, which clearly exposes sections of the overburden. The glacial debris is yellow, overlying the grey Cretaceous shale. At present, it's uneconomical to dig deeper than 150 feet to extract the tar sand. This accounts for the wide difference between the potential recoverable quantity and the current recoverable quantity, which is only about 10%. The first step in the excavation is clearing the tamarack swamp and the underlying 25 to 20 feet of muskeg. Water must be drained off in ditches which are dynamited. Water is then left to run off for about 2 years. Clearing the muskeg can only be accomplished in winter when the ground is frozen. Otherwise, the 150-ton trucks that haul the muskeg away sink into the ground. Once the muskeg has gone, the glacial boulders and the sand and the gravel and the Cretaceous shale can in turn be stripped off. In the Great Canadian Oil Sand Company's operation, this overburden is then put to use in building 300-foot retaining dikes to hold the tailings from the extraction plant. Over the next 10 years, 21 150-ton trucks will move about 13 million cubic yards of overburden per year. With the overburden gone to the dikes, the oil sands are exposed. The Great Canadian Oil Sand Company has 2 massive self-propelled bucket wheels that scoop the black sand to a conveyor system. The bucket wheel itself is 33 feet in diameter, and the machine stands about 10 stories high. It's electrically powered and weighs 1,800 tons, about the same as a couple of dozen jumbo jets. The teeth of the buckets are about 120 per bucket, each one weighing 100 pounds. Each of the two excavators moves an average of 4,000 to 5,000 tons of tar sand per hour and is operated by only one man. It takes about 2 tons of sand to yield 1 barrel of bitumen. The conveyors have a speed of about 12 miles per hour, and the main belt is 6 feet wide and almost a mile long. Keeping the machinery in operation is something of a problem. In the heat of summer, at perhaps 85 degrees Fahrenheit, the sticky tar sand gums things up, and in the winter it freezes as hard as rock. When the excavation was first attempted in the winter, the teeth of the buckets glowed red and tore off within 4 hours. The conveyors drop the oil sand into a storage bin at the extraction plant, but only for an hour, until it begins the first stage of the steam and hot water and caustic soda separation. The fine sand which settles out in the hot water is pumped to the tailings pond, and the bitumen at this point still contains sulphur and nitrogen and some heavy metals. It's thick and viscous and not immediately usable. Heating of this heavy bitumen during refining leaves coke, a carbon-rich product. The light hydrocarbons driven off during coking are what is recovered by condensation. This crude oil is much lighter, and it can be further refined for any number of uses. At this stage, the sulphur in the original bitumen is driven off. And the final refined product is much more like the gasoline that we know. One of the main byproducts is of the sulphur. It's currently being produced at about 350 tons per day. There's no market for this quantity, and the accumulating pile is something of a problem. It's a problem shared by mines too. Sulfide ore also produces sulfur in vast quantities. The other major byproduct is coke. Most of this is used in the refining process as a fuel. Over 2,000 tons of the 3,000 that are produced per day are in fact used on the site. But this results in yet another problem, since the coke is also high in sulfur, and when burned it releases sulfur dioxide. Like many other refining processes, there's still room for technological improvement. The other waste problem is the liquid waste, the tailings. They're pumped from the extraction plant to tailings ponds at about 24,000 gallons per minute. Being so close to a major river, adequate dike construction is critical in order to hold this water, which is by far from pure. As well as revegetation of the mined out area and the tailings, the protection of the watershed is one of the major concerns of the tar sand operators. And when the operation gets bigger in the future, it'll become an even greater concern. The $2 billion Syncrude operation on Lease 17 will eventually extend over 12 square miles, covered on average by 5 feet of muskeg and 80 feet of barren overburden. Beneath that, the tar sand averages about 150 feet. Once again, the mining method is open pit, but instead of bucket wheels, Syncrude will use 4 80 cubic yard capacity draglines, about 5 times the capacity of this experimental dragline. Plans call for the plant to be in operation by 1978, and then it should eventually produce 125,000 barrels of crude per day, and that rate should continue for 25 years. Syncrude's test pit is quite interesting and shows a number of geological features of the tar sand. At the lip of the pit, as always, are the brown glacial gravels, and beneath them, Cretaceous shale. The upper part of the tar sand itself is also regarded as an economic overburden, since this higher part usually contains less than 8% of bitumen, which is a minimum level for economic recovery. The richest beds are always found towards the base of the tar sand, where bitumen may be as high as 18%. The grain size differs at various places in the sand, and this is what marks the bedding in the sand. The sand, in fact, is much coarser towards the base until the grain size reaches pea-sized pebbles. The black bitumen should not be confused with oil. Although it is a hydrocarbon, and a liquid hydrocarbon like oil, it's structurally different, so that it has to be altered during refining, or cracked in oilman's jargon. What essentially happens is that hydrogen is added. The sands are not well consolidated, despite the steep pit sides which can be cut in it. There's quite a lot of water as well as bitumen between the grains. In fact, each grain is coated with a film of water, and that in turn by a film of bitumen. This is what makes the tar sand so hard in winter. Crossbedding and channeling in the sands is conspicuous and evidence of the waterborne origin of the deposit. In this case, the water flowed from right to left. Another unconventional source of oil is so-called oil shale. The most extensive high-grade deposits in North America, and probably in the world, cover about 16,000 square miles at the border between Utah, Colorado, and Wyoming, about half the area of the Alberta tar sands. They've been estimated to contain about 450 billion barrels of potential oil, of which it might at present be practical to recover about a sixth, about 80 billion barrels. These shales, the so-called Green River shales, were deposited in a large saline lake about 40 million years ago in Eocene time. Abundant fossils indicate that the shale was originally an organic ooze, rich in pollen and partly decayed plants. The rock itself is a fine-grained sedimentary rock, with the organic matter giving it a dark color. In contrast to the residual bitumen in tar sands, oil shales contain organic material that's not yet been converted to oil or gas. And to do this requires temperatures of over 900 degrees Fahrenheit and extensive processing. The processing requires about 100 gallons of water for each gallon of oil recovered, a large demand for the arid area in which these oil shales occur. In this pilot plant set up in 1965, these shales are mined underground. Mineable layers are considered to be those about 100 feet in thickness, and the oil shale is carried out to the processing plant in 80-ton trucks. Underground, a scraper breaks away the oil shale from the sides of the drifts. The mining methods underground are quite closely similar to those used in a metallic or a conventional mine. The shale is drilled and dynamited, but it's difficult to see this being an economic process in the near future. Most other oil shale is recovered in open pits. The miners leave the drifts during the dynamiting of the ore. And the same kinds of techniques as in conventional mines have to be used to secure roofs, for example. Roof bolts are here being inserted to make sure that fragments of the oil shale don't fall to the floor of the drift. The initial stage of the processing requires the crushing of the shale, in order that later on the heat can drive off the organic matter which is contained between the silt and the mud particles of the rock. The essential part of the process after the crushing is the heating of the oil shale. It's preheated before it's mixed with hot ceramic balls and then rotated in a drum. This drum results in the driving off of the hydrocarbons, the organic matter in the shale. The ceramic balls in the slowly rotating drum are at temperatures of several hundred degrees Fahrenheit. The vapors are then led away and condensed. One of the problems is getting rid of the waste, but the oil itself is immediately usable. The refining of oil shale continues and rather hurries along a process that had begun in nature. That is the formation of hydrocarbon molecules from the organic material of the dead matter in the shale. Now, once that has occurred in normal oil, the oil then goes through a second stage, a stage of migration from the source rock into a reservoir rock. In these diagrams, the oil is the orange layer. Above it is gas, beneath it is water, and it's found in sandstone between shale layers. This is the reservoir rock, characterized by its porosity, that is space between the sand grains, and the shale is characterized by the inability to allow the oil to pass through it. So the oil is trapped in the reservoir rock, in this case in an anticline. In the Persian Gulf, oil is trapped on the flanks of salt domes, which push up through the overlying rock, trapping the oil on the flanks. An interesting byproduct of the movement of the bitumen into the tar sands in Alberta is fossil wood. Wood that's been soaked by bitumen. It looks rather like a creosoted fence post, but in fact that wood's about 100 million years old. The normal way to find wood is mixed with other partially decayed plant matter as coal, which far overshadows oil as a resource of fossil fuel. In the United States, there are about 8 trillion tons, of which only about 2% has been used. In Canada, there are also vast quantities of coal, particularly in the western provinces. Where the coal seams are not more than 50 to 100 feet below the surface, the overburden can be stripped away, just as it is in the tar sands, and almost all the coal recovered by open pit mining. This is the major mining method for recovering coal in the west of Canada, as described by Dr. Follansby of the University of Alberta.
The coal seam is buried beneath 20 feet of glacial drift and 30 feet of pre-glacial gravel. These gravels were rolled down from the mountains 500 miles to the southwest and form a valuable byproduct of the mining operation. This coal seam is an immense resource. 23 feet thick, it represents 30,000 tons per acre, and the seam runs for 200 miles down across the Saskatchewan and the Red Deer rivers, north to the Athabasca. It can be mined across a belt 12 miles wide. Ultimately, it will produce as much power as Niagara Falls. It will be the principal source of power in this province for generations to come. "63 million years ago, this area around Lake Wabamun was a great swamp, very much like the Everglades of Florida at the present time. In this swamp, giant trees grew and finally were buried in muds that flooded down from the rising Rocky Mountains to the west. Here at the bottom of the section, we see a shale parting. Brown shale, brown muds that came in off the mountains and buried the coal. At this point, the coal seam reestablished itself, the forest grew, and we have here 3 feet of coal. This represents 30 feet of forest peat, compressed and squeezed by the weight of the overlying sediments. Here we see a bright spot of amber, representing fossil pitch, the gum of the spruce trees that lived in the Bitumen swamp. On the death of the tree, the fossil gum hardened into a yellow, translucent gem mineral, and we have a zone of amber in the bottom of this part of the coal seam. At this point in the section, we have a minor catastrophe. 1,000 miles to the west, a volcano blew its top, and a giant ash cloud came across the western prairies and settled onto the swamp, completely destroying it, killing many of the dinosaurs. This is the end of the age of dinosaurs. We can visualize perhaps the last of the dinosaurs choking and gasping for breath in this giant cloud of dust that settled down over the swamp. Once again, the volcanoes became quiet and the forest reestablished itself to lay down the last and upper member of the Bitumen coal seam. It's a 6-foot layer of coal which finally was buried under overlying sandstones and gravels. So here we have a record then of the close of the age of dinosaurs and an accumulation of coal, lignitic coal, that amounts to many billions of tons and which contains far more energy then than all of the oil that has so far been found in Canada. This coal seam lies on the borders of one of the most beautiful of the recreational lakes in the Edmonton district. And Calgary Power has made an effort to restore the land by reclamation. The dragline material is smooth and reseeded with alfalfa, and within 2 years, the land is in somewhat better shape than it was at the beginning of the mining operations.
The world's resources of coal will probably last 3 or 4 centuries, and of oil and gas perhaps another century. And Canada's vast resources of coal and of tar sand, providing the technology can be developed to get the tar out of this sticky sand, will put her in as least a good a position as any other country to deal with the problems of what to do when the oil and the gas become difficult to obtain. The other major advantage that Canada has is her richness of metallic ores, and everyone in Sudbury knows that Sudbury is a big producer. In fact, Sudbury could probably qualify as the greatest mineral producing area in the world. Sudbury doesn't only produce copper and nickel, but is also the world's largest platinum producer, for example, and produces a dozen or so other elements. And the interesting thing about the Sudbury area is the geological structure with which the ore is associated. On this geological map, you can see that the rock types represented by the colors are in a circular or elliptical arrangement. The outer part, the outer 2 bands, represent the hilly rim of the basin, and the gray area in the center represents the flat area. The rock types are different from margin to center. If you look at the basin from the air, then the village of Dowling, for example, shows how flat the structure is in the center. And looking from the center towards the rim, then the hilly rim of the Sudbury Basin is very obvious. The form of the Sudbury Basin can also be seen from high points either on the rim or just outside. One of the best vantage points is from the basalts just outside the basin, close to the Murray mine. From this point, the hilly rim can be very easily seen to the north and to the east of the basin. The flat area in between is the lowland occupied by farmland in the center of the basin. The rock which forms the margin of the basin is dominantly an igneous rock, one we looked at in the igneous rock unit, and you'll remember that it shows differentiation very well. That is the separation into two distinct kinds of rock, but a gradual separation, the pink micropegmatite and the rather dark norite, produced by the crystal settling of early formed dark iron and magnesium-rich minerals. The other rock of the rim of the basin, also a very resistant one, is exposed in the Onaping Falls. This is the Onaping breccia, and it receives its name, in fact, from its very easily visible occurrence at the Onaping Falls and along the banks of the Onaping River. It's a different kind of rock to the igneous rock. In fact, it's formed of fragments. Fragments that you can see in this hillside as white patches. These white patches, actually boulders and pebbles and fragments of all different sizes, can sometimes be quite closely compared with rocks that occur now outside the basin, which must have occurred in the subsurface when the basin was formed. This whole rock is formed of fragments of all different shapes and sizes, some of them showing smooth outlines because they were possibly hot at the time. Looking back across the basin towards Sudbury, one can see the smokestacks of the nickel refinery at Copper Cliff, or the nickel smelter at Copper Cliff. Looking again across the flat center of the basin. The center of the basin is occupied, remember, by the Chelmsford sandstone, a dark sandstone thought to have been deposited in the basin after it was formed. Here, the rock is bent into a gentle anticline, indicating the deformation of the basin after its formation. Further evidence of the deformation can also be found in the Chelmsford sandstone in the form of fractures or rock cleavage. This developed clearly after the sandstone was deposited and consolidated as a rock. And the basin, in fact, was squeezed. You can think of the basin as a soup bowl with the Chelmsford sandstone in the center, and then if it were formed out of clay, imagine the soup bowl being squeezed a bit, and the contents being folded and fractured, and the actual rim of the basin being made much steeper than it originally was. So that basin was quite certainly fractured after it originated. The outside rim of the basin is the ore zone, exposed along Highway 144 between the road and the railroad. The train here is just about to go past the so-called discovery site where the ore was first recognized for what it was. The ore zone is quite narrow. It's never much broader than the outcrop that the train is just passing now. This eventually became the site of the Murray mine. That was in the late 1880s and the early 1890s. The ore zone is very weathered. It's brown and rotten looking because the iron sulfide, the pyrite in the ore, easily oxidizes. And it produces sulfuric acid, which dissolves the copper sulfide in the ore, producing a very rotten-looking rock. It's only possible to find fresh sulfide samples on newly broken surfaces. These are pits dug in that rotten ore zone. The ore was, in fact, very easily recognized during the early days of prospecting simply because of that rotten, rusty color on the surface. And in fact, the rusty color is just that, rust. those early pits, now filled with water, are in fact quite dangerous. On the sheer surfaces of that discovery site outcrop, one still can see the shiny sulfide ore, contrasting with the black rock, but only, remember, on fresh surfaces. Fresh pieces of ore from underground show even more clearly the relationship between the copper-nickel sulfide ore and the silicate rock. Cutting the ore through with a diamond saw shows the shiny sulfide in considerable contrast to the rather dark color of the rock. Cutting a thin section shows that relationship even better. A thin section cut in the normal fashion and ground so thin that light will pass through it. If we take such a thin section and look at it under the microscope, the silicate mineral grains are quite clear and crystalline, and the sulfide lies between them and is the dark mass in the center. Crossing the polars of the microscope makes that even clearer. But front lighting is much better for distinguishing the various sulfide minerals, because there's not just one. Pyrrhotite, an iron, nickel, and cobalt sulfide, is an important constituent of the Sudbury ore. Chalcopyrite is the copper sulfide present in the ore. And finally, pentlandite, which is the main source of the nickel, is an iron-nickel sulfide. In order to understand how the ore and the rock came to be associated, remember that the atoms, when the rock and the sulfide were hot, were vibrating because of the thermal energy, the heat of the mixture. And as it cooled, the atoms were able to form bonds. In the case of the silicate minerals, it was iron and magnesium and oxygen silicate tetrahedra, which formed bonds in order to make such minerals as pyroxene and amphibole and so forth. But there were also bonds forming between sulfur atoms and iron and magnesium. And those bonds formed the sulfide lattices. Here, the pyrite lattice, the large atoms being sulfur and the small ones being iron. And this lattice, repeated, forms the sulfide ore in the rock. And put simply, the metallurgist's job is to release the ore from the rock by breaking the bonds between the ore and the rock, the mechanical bonds, and by melting the rock and the ore. Smelting is an old process. It was already used 2,000 or 3,000 years ago. It can be illustrated in this crucible. The melting of the ore and the rock causes the rock to float to the surface and the heavy sulfide to sink to the bottom. It's a continuation of the same kind of process by which the ore originated during the cooling of the igneous rock. The first task in producing pure metal from the ore is to break the mechanical bonds between the sulfide grains and the silicate grains. This is accomplished in the crushing and the grinding process. This breaks the mechanical bonds. It's now done in quite sophisticated equipment, and the ore is broken down to a constant and controlled size, eventually down to about 1/100th of an inch. This is accomplished in mills, rotating drums containing steel bars or balls. In this way, the silicate crystal grains and the ore, the sulfide crystal grains, are released from one another, and therefore it becomes possible to separate the rock, which one doesn't want, from the sulfide, which one does. Here the rods are tumbling inside one of the grinding mills. The ore then looks like a pulp, the ground up ore and rock. and it can be separated. And constant analysis of the separation can go on, controlled by computer, at the same time as the remaining material is going through the smelting and the separating process. The control rooms of a modern mine look rather different from the headquarters of mines not so very long ago. Here, the waste product being poured away, the slag that's such a familiar sight to tourists and to the residents of Sudbury. And these are the rocks of the Sudbury Basin. The ore, the very rich sulfide ore, and the rocks of the igneous rim, the pink micropegmatite and the rather darker norite, and then the Chelmsford sandstone, the rather dirty sandstone, which fills the center of the basin and which we don't find anywhere else. Now, those are relatively easy rocks to explain. Although the ore is obviously very rich, it's quite commonly associated with igneous rocks such as we find in the basin. But the really peculiar rock is the one that's found at Onaping Falls, the Onaping breccia, which is formed of fragments of rock. You can see one or two lighter patches on this specimen. It's that Onaping breccia which brought the astronauts to Sudbury and which gives us some clues as to the origin of the basin. You may remember from Unit 14 that we compared the Sudbury Basin to a meteorite impact crater, and it was that rock, the Onaping breccia, which brought the astronauts to Sudbury to look at it as perhaps evidence for that meteorite impact origin of the basin. If the basin is a meteorite impact crater, then the story probably runs like this. About 2 billion years ago, the impact of a large meteorite, perhaps several kilometers across. After the impact, immediately after the impact, a great deal of material thrown out, which fell back into the crater as a layer of broken fragments, the Onaping breccia. And beneath the crater, melting took place, molten rock welled up into the bottom of the crater like a pool and floated up those fragments. This is the igneous rock that now forms the rim. Then the next stage, the filling of the crater with this upper layer here, the green layer, the Chelmsford sandstone, and of course the erosion of the crater walls. And then finally the crumpling of the originally round crater, or the squeezing of it to give it its present elliptical form. That's one suggested series of events for the origin of the basin, beginning with the impact of a meteorite. Now, there's another possibility too. That same Onaping breccia can be interpreted not as the fallback breccia of a meteorite impact, but as volcanic material. And in that case, the sequence of events would run like this. A volcano in the Sudbury area about 2 billion years ago, and we know there were volcanoes in this area at about that time. During a very violent explosion, after the volcano had been stoppered up, as it were, by the solidification of lava in its neck for some time, during a very violent explosion, the volcano was broken up into fragments, which sank back into the molten material beneath the crater. Here, the fragments sinking into that molten material, and the fragments of the Onaping breccia accumulating in the crater. And then the disruption of the shape of the crater, and also, not shown on this diagram here, the accumulation of the sand and mud that would now be the Chelmsford sandstone in the center of that crater. Two alternatives, both of them the product of a very violent event. And we're pretty certain that there was a violent event that caused the origin of the basin, and the grounds for that lie in evidence that the rocks in the Sudbury area have suffered from shock. In order to find that evidence, we must look outside the basin, beyond the ore zone exposed in the railroad, to the rock that was in place before the Sudbury Basin was formed and before the ore zone originated. These are such rocks to the south of the basin, And in them we find strange structures called shatter cones. Cone-shaped fractures within the rock, here about 2 feet tall, produced, so far as we know, only by very violent explosions, such as nuclear explosions, and perhaps by meteorite impacts. As well as the shatter cones, we also find what are called fissure breccias, and they're well exposed on the road north of Levack, north of the basin. Such a small fissure breccia is here with a dark ground mass and light fragments, the fragments being derived from the edge of the fissure. It seems as though the ground was broken up and boulders of granite in the north of the basin, where the country rock is granite, fell into the fracture and were ground up together to produce a rock flour ground mass, which is rather glassy and therefore dark. The fissure breccia, formed by the pulsing jaw crusher action of the broken up ground during the explosion, doesn't really tell us whether the basin was produced by a meteorite impact or by a volcanic explosion. It's simply not diagnostic enough. Even the shatter cones, which were once thought to be diagnostic of meteorite impact or nuclear explosion, are no longer thought to be as convincing. The best evidence probably does lie under the microscope. The fractures in this quartz crystal, shown as lines, are probably the best indication of very high shock pressures, but even that's not as certain as it once was. Whatever the origin of the basin, and it must remain at the moment enigmatic, the value of its ore and the richness of the metal deposits in Sudbury is not in any doubt at all. Last week we looked at some film of the early mining methods. Let's end by looking at the way that the ore was smelted at the beginning of this century. In a typical mine at that time, getting the ore to the surface for smelting entailed first measuring it out from the underground loading bins into large ore buckets or skips, each skip taking about 4 tons of ore, and the skips themselves weighed 3 tons. The skips and the ore were hauled to the surface using a system of counterbalances, a heavy counterweight drawing the skip to the surface to the first step of the processing. In this stage, the ore went through a series of crushing and sorting operations rather dissimilar to those employed today in getting the ore ready for smelting. The purpose then is now being to separate the barren rock from the sulfide ore. On picking belts, waste rock, low-grade ore and high-grade ore were separated, not an operation that one sees very often today. Once sorted out from the rock, the ore was sent to the Mond Nickel Company's smelter at Coniston, about 8 miles east of Sudbury. The smelter, built in 1913, about 2 years before this film was made, was the most up-to-date in the Sudbury area, which hitherto had been devastated by the open roasting of ore. The Coniston town site, built for the smelter workers, was already a rather bleak place. The smelter was closed down in the early 1970s in favor of the Copper Cliff smelter to the west of Sudbury. But in 1915, Coniston was the smelter to which all the ore of the Mond Nickel Company was sent. The ore which entered the smelter was first weighed in the car in which it arrived. Production of ore was generally ahead of what the smelter could handle, and much of the ore was simply stockpiled in the storage yard. Working at full capacity, the smelter could probably handle about 3,000 tons of ore per day, a very large figure for that time. Everything in 1915 was working full out to satisfy the wartime demand. One of the metallurgically most interesting advances in smelting technology employed at the Coniston smelter was flotation. In this process, the low-grade ore was first taken from the storage yard to the flotation mill. Ore which contained only about 15 or 20 pounds of nickel and copper sulfide per ton had previously been rejected, but it was now enriched in the flotation mill. After crushing and grinding, the low-grade ore was passed over concentrator tables as a fine powder. The water washed the lighter waste rock material to the sides, and the sulfide ore came out as a slurry at the end. And then it was mixed with pine oil and sulfuric acid, and the sulfide particles floated to the surface with bubbles of air introduced by the paddles. This is a process common today. The very fine ore dust produced by flotation was not suitable for the furnaces, and Mon Nickel therefore roasted the fines, as they were called, in a sintering plant. This differed from the process employed at Copper Cliff. The sintering plant needed to be carefully loaded, the coarse grains at the top and the fine at the coarse grains at the bottom and the fine at the top, so that the sintering beds would burn when the oil blast was forced through the porous ore. In this way, the particles were bound together, and about 15% of the sulfur in the ore was lost, driven off as sulfur dioxide. The sponge-like sinter was much better furnace fuel because of its porosity, and furnaces were the next stage in the smelting process. First, the ore was transported from the sintering plant to the furnaces, usually again being kept in storage bins until the furnaces could accommodate it. The furnaces were the central part of the smelting process, the aim not being to produce pure copper and nickel, but to produce a so-called matte, low in sulfur and rich in metals, which could then be chemically or electrolytically refined. This last stage was carried out in Wales, in the United Kingdom, where Mond had built a plant for the nickel refining process he invented. High-grade ore direct from the storage yard and sinter from the roasting plant were mixed with limestone and coke and burned in the furnace. Coniston had 4 furnaces, each with a capacity of about 750 tons per day of ore, averaging about 4.5%. The principle of smelting was an old one. The limestone added in the separation process acted as a means of floating off the waste rock, which came out as slag, which was then poured onto the slag dumps, an operation that many visitors to Sudbury and many Sudburians see every day. About 1,000 tons, or 25 slag pots, each holding about 4 tons, were poured onto this slag dump every day. This was the initial separation of the rock, the waste rock, from the ore. The nickel and copper sulfide still remained to be separated from the iron. At the same time as the rock floated to the surface in the settler, the metal sank to the bottom. This enriched the ore from about 4.5% to 16%. Quite a deal more enrichment still needed to be done, but first the furnace matte, rich in metals, was drawn off in great ladles, 15 tons of molten metal being taken at a time from the so-called settler. The further enrichment of the cool metal was similar to that of the blast furnaces, quartz being added in order to combine with the iron, which was the unwanted sulfide, and so enrich the final matte in copper and nickel. Oxygen was introduced at this stage to burn off the sulfur, and then the final matte was poured off to cool. The matte now consisted of about 80% copper and nickel. After cooling, the ore was broken, or the matte was broken and crushed, and it was this product which then went to be refined. And it was the refining which, of course, posed the big problems, the separation of the copper and the nickel. The matte was always crushed to a powder for transport and for selling, and loaded into barrels. something in the order of 20 million pounds of nickel and something less copper were produced each year in the Sudbury area around about 1910. It was not until later that refining plants were available in Canada for the refining of this matte. Before it ever became nickel or became incorporated in steel plates, this matte had to go as far as England. One of the large refineries which took over from this was in Port Colborne, a refinery that's still operating. The ore first transported to the Atlantic coast for shipment to England. Repair shops on the surface were well equipped for the repairing of machinery. Increasing mechanization and the introduction of electricity gave the repair shops plenty of work to do, particularly compressors for producing compressed air to drive the forges and the skip brakes and the drills and also some air cranes. This kind of equipment needed to be maintained. As well as repair shops, there were also metallurgical laboratories. And of course, the larger equipment needed to be maintained. In the metallurgical laboratories, analyzing the matte was the principal task. It was important to know just how efficient the smelting process was. It was surprising how many advances were made in the smelting process and also in the refining process quite by accident. One important discovery in the refining process was made when a janitor cleaned up the chemicals from the bottom of the chemical store and poured them into the furnace. Drills were an important part of the underground equipment, and their maintenance was an important task for the repair shops on the surface. The drills quickly became dull, and the principal job, of course, was to sharpen them and retemper them at both ends, and also to clean out the hole in the center of the drill through which the water came to cool the bit. The difference between a dull and a sharp drill can quite easily be seen. The typical form of these drills can still be seen in the rocks around, for example, cobalt. Many of the scenes on the surface are similar to those of today. There are many people who are familiar with this scene at least twice a day. Although perhaps the water is now a little hotter.